here looking at the Pythagorean Theorem. We're putting it in reverse and heading back to 500 BC, where Pythagoras told us how the sides of a right triangle are related. You've heard it stated in your geometry class that a squared plus b squared equals c squared. The Pythagorean Theorem is going to enable you to solve for a missing hypotenuse, which is always across from the right angle, or missing leg length in a right triangle. If you're looking for the hypotenuse, you're going to square the side lengths, add them together, and take the square root. Or, if you're looking for a missing leg length, you're going to square the hypotenuse, square the leg length, subtract, and take the square root. But on the ACT, you're going to need to work more efficiently. The Pythagorean theorem is relatively simple, so why not skip to the last step? Let's look at an example. Instead of setting up the Pythagorean theorem, then solving, just remember that the hypotenuse is the longest side in a right triangle. You'll be adding to find the length of the hypotenuse, and the shortened setup looks like this. Similarly, if you're looking for the leg of a right triangle, no need to work through several steps. A leg is shorter than the hypotenuse. You'll be subtracting to find the missing leg length, and the shortened setup looks like this. Remember, add to find the length of a hypotenuse and subtract to find a leg length. On the ACT Maths section, you're going to have to work 60 problems in 60 minutes. If you're setting up long equations or working through several steps, you've probably not spotted the quickest path to the solution. Let me show you another way to really save time. One of the best strategies for saving time when working with right triangles is to know the three big triplets, or Pythagorean triples. These are simply sets of whole numbers that work well with right triangles, and the test makers use them to write right triangle problems because they know when they use these triples, the side lengths will turn out to be whole numbers. Here are the three triples that show up most often: the 3, 4, 5 right triangle, the 5, 12, 13, and the 7, 24, 25. Now these triangles can be disguised. They can be scaled up by a factor of 2, 3, 4, and so on. For instance, the 3, 4, 5 triangle can be scaled up by a factor of 2 and show up as a 6, 8, 10. Or tripled to become a 9, 12, 15. Or even multiplied by 10 to become a 30, 40, 50. So when you know these Pythagorean triples, you don't have to set up the Pythagorean theorem on every single right triangle item. For example, if you are given the side lengths of 5 and 12, you know the length of the hypotenuse is 13. And you don't need to use the Pythagorean theorem. So how will this look on the ACT? Many times, these items are straightforward. You'll be asked to solve for the missing side length in a right triangle. Here, you are given a leg length of 5 and a hypotenuse length of 13. You know the missing length is 12, and hopefully, you didn't have to set up the Pythagorean theorem at all. But often, these triangles are paired with other concepts. You may be asked to find the length of a diagonal. In this case, you'll have to actually use the Pythagorean theorem, because this is not a Pythagorean triple. Let's use the shortened Pythagorean setup we learned earlier, and then simplify to find the diagonal length. The right triangle may be embedded in a circle, where you'll need to rotate the radius to form a right triangle. The chord length splits in two, and voila! A 3, 4, 5 right triangle appears. Or, if asked, you can easily find the circumference or the area. Test makers may even lean a ladder against a wall and ask you to find the length of the ladder. Hopefully, you recognize the 7, 24, 25 Pythagorean triple. Or, they may ask you to set up a trig ratio with the triangle.
If you've forgotten your trigonometry, then watch the triangle trigonometry video.
On the ACT, look for common Pythagorean triples, the 3, 4, 5, the 5, 12, 13, and the 7, 24, 25. And know, they are often scaled up. And if it's not one of your Pythagorean triples, then utilize the Pythagorean theorem.